Hi, welcome to session 2 of Graph, Homomorphisms and Universal Algebra. Luckily this is an online course, so you are all safe behind your screens at home and we don't need any extra additional hygienic measures. Today we use another great feature, namely I can draw into my PDFs. So the topic of today's course is the arc consistency procedure. Before I go into that, let's briefly recap what we've seen last time. We introduced the class CSP of H, which is the class of all finite digraphs G that homomorphically map to H. And we would like to understand for which graphs H can we decide efficiently for a given G whether G homomorphically maps to H. For which graphs H is this class easy, and for which graphs H is this a complicated class. And one of the most fundamental algorithms in this context is the arc consistency procedure. It's important both from a theory perspective and from a more applied perspective. From a theory perspective, it's important because it has many very elegant characterizations. So we have nice descriptions of those graphs H where CSP of H can be solved by arc consistency. From a practical perspective, this is a very good algorithm. We'll discuss this in detail, but this is really one of the algorithms where theory meets practice. Let's illustrate the idea. Arc consistency is a special case of a local consistency algorithm. There's a very easy idea behind this. So we will perform local inferences and then repeat, making local inferences until maybe we find a contradiction, in which case we say the CSP is unsatisfiable. And otherwise, we hope that there is a solution. And you all know this principle from Sudoku. Let's look at a super silly Sudoku. I've drawn you this. So please look at the first row. The first row, remember the constraints say not, one value should not appear twice. Every value should appear exactly once. So this forces us to fill this front entry with 9. It's the only value which didn't show up yet. And then if you iterate, you can make further inferences. So if you look at the first column now, we have eliminated all except for 1, so the last field must be 1. You see the idea. And since it's so natural, it appeared relatively early in the literature. So in artificial intelligence, in AI, this was discussed in various contexts, this method. Let's look at a more interesting example. Of course, this is not the only type of local inference that we can make. And usually it's better to take a negative perspective. What do I mean by that? Let's look at the first entry. The top left entry, this one. Imagine for each entry we have a big bag of possible values. 9 of them in our case. And now local inference means that we eliminate candidates from this bag. We'll do that eventually for all bags, but for all fields, but let's illustrate it for the top left. The first row, the constraint there the constraint for the first row effectively eliminates all even numbers as possible values, because the even numbers already show up. Now, the first column can be used to make local inferences as well, and it effectively eliminates some more values, 9, eliminates 9. 7 already shows up, so 7 can't be the value. 5 is eliminated, and 3. And oh, we see only one value remains. So this is why we can add here value 1. We know every solution must map this field to 1. And the very same idea, if you repeat and repeat, the very same idea can be used to attack graph homomorphism problems. So suppose we are interested in CSP of P2. Oops, P2. And suppose we are given the following graph G in the input. First, let's give some names to the vertices of G. So let's call this bottom vertex A, the next vertex here B. For each of the vertices, we imagine a bag of values 0, 1, 2, the vertices of P2. So this is the bag for A, and now we look at P2. Is it really possible that A is mapped to 2? The thing is, there is an edge from A to B, so we would also have to map B somewhere. But the vertex 2 has no outgoing edge, so there's no candidate. So in fact, value 2 is impossible for variable A. So that's why we eliminate 2. Completely analogously, we can reason for B. Also, B has a bag of values 0, 1, 2. And also here, for the same reason, it's impossible that variable B is mapped to 2. Now, this inference in turn allows us to make another inference for the bag for A. Because we know B can't map to 2. So I claim A can't map to 1. Because if you send A to 1, you would need a neighbor which can be sent to 2. But B can't be sent to 2. So we can eliminate the value 1 for A. Note that this is really a reasoning where we iterated local reasoning. And now continue like that. It's a nice exercise to continue like that and to see how far can you eliminate values from these bags. And finally, here comes the source code, the pseudo code of the arc consistency procedure. So again, we start with some fixed finite digraph H. The arc consistency procedure depends on H. The input is a graph G. And these bags, well, here I call them lists, yeah, or actually these are just sets. For each variable x, I maintain a set of vertices of H. In the beginning, all of these sets are largest possible. So all vertices of H are in the bag, in the L of x for every variable or vertex x. Now we have this loop. This is this iteration loop for the local propagation. And I do this local propagation for each constraint, which is for each edge in G, x, y. I know u is impossible as a value for x, and I remove it, if there is no candidate for the neighbor, y of x. There is no vertex v of H, so that the pair of values uv would form an edge in H. This is precisely the type of inference that I have made on the previous slide. And there's a symmetric, a dual version, which I star here. It's just following the arcs in the other direction. If at some point I find an empty list, I know there's no value left for this variable. So this makes it impossible that there's a homomorphism from G to H. So correctly I can reject. There's no homomorphism. And this we repeat and repeat and repeat until nothing changes anymore. If the algorithm rejects, clearly there is no homomorphism. If the algorithm does not reject, then we have to have a closer look. Arc consistency has many nice properties. The first I would like to mention is that you can implement this algorithm so that it really runs very efficiently. It runs in linear time. For fixed h, it runs in time that is linear in the size of the graph G. That's very nice. So if the input is twice as large, the algorithm runs at most twice as long. This is very desirable. It has only linear memory space. We just have to store the bags. It's very easy to implement. You've seen the complete pseudocode on the previous slide. Moreover, it does not only work for digraphs, it can be easily generalized. You've seen the initial example for Sudokus, and in the second part of this course, we'll generalize it to its natural scope. On the other hand, note that it is only a one-sided test, in the sense that if the algorithm says reject, we can be sure there is no homomorphism. If the algorithm does not reject, unfortunately we don't know. So we say the procedure might be incomplete. Elsa, ich mache gerade eine Aufnahme. Du musst mal kurz warten, bitte, okay? So the procedure might be incomplete. It might be that there is no homomorphism to H, but the arc consistency procedure does not detect it. It does not derive the empty list. And a very good example is this little problem here. We have C5 directed version and C6 directed version. And we immediately see how should there be a homomorphism from C5 to C6. There is no homomorphism from C5 to C6. But the arc consistency procedure can't make a single inference. So it will not say reject here, unfortunately. On the other hand, if you're lucky, and this depends on the graph H, there are some graphs H where arc consistency derives false, derives the empty list, if and only if there is no homomorphism from G to H. In this case, we say arc consistency solves CSP of H. For instance, we'll see in the following. Arc consistency solves CSP of P2, or more generally, CSP of PK. It solves CSP of T3, of TK. On the other hand, it does not solve CSP of K3, and I wrote here no surprise. Why? Well, we've seen arc consistency is an efficient algorithm. CSP of K3 is NP complete. So many times I said it's very unlikely that there is an efficient algorithm for CSP of K3. So it's no surprise that arc consistency does not solve CSP of K3. And we have already seen on the previous slide, arc consistency does not solve CSP of K6. So CK in general, actually. And the central question now is, can we characterize those graphs H so that arc consistency solves CSP of H? Can we understand the scope of this algorithmic method? And there's a very nice answer to this. Yeah, I had a lot of feedback. One of the feedback points was, what happened to the blackboard cleaning break? And indeed, breaks are important. So in particular in Corona times, yeah, your sport program is a little bit limited. I have one suggestion for you. Please join me. The key tool to understand the power of the arc consistency procedure is the power graph, or the Powerset graph. It's defined for every digraph H, and the vertices of the Powerset graph for H is the set of non-empty subsets of the vertices of H. We put an edge if and only if the following condition holds. Suppose we have two of those subsets of the vertices of H. And we want that if you draw the edges between these vertices as they are in H. In this example, it will be P2, the directed version, but we'll do the example later. But let's first look at the definition. I want that for every vertex in the first set S1, there is a vertex in the other set S2, so that there is an edge between those two. That's the first bullet here. The second bullet is for every vertex in S2, there should be a vertex in S1 so that they form an edge. In other words, what I don't want to see is something that some vertices in one of the two sets, S1 or S2, is lonely, has no neighbor here. This would, for instance, in this example which I've drawn on the left here, S1 prime, S2 prime, there would not be an edge in the Powerset graph because I see lonely vertices. On the other hand, this first example, S1 and S2, satisfies the condition, so here I would make an edge in the Powerset graph. So let's really look at a concrete example. We have here P2. P2 has 3 vertices, so there are 7, 8 minus 1, non-empty subsets of 1, 2, 3. I've drawn them here. Now let's look at an example. Here I have the set 1, 2, and here I have the set 2, 3. There's an edge from 1 to 2 and an edge from 2 to 3. So in the Powerset graph, I would put an edge between 1, 2 and 2, 3. Now let's look at 2, 3 and 1, 3. I have certainly an edge from 2 to 3, that's fine. But then 3 is lonely. There's no outgoing edge from 3, so there would not be an edge in the Powerset graph here. Well, I have 2 more edges. I have them on between singleton subsets. So here I have, for instance, the singleton subset 1, just contains the vertex 1. The singleton subset 2 just contains the vertex 2. There's an edge from 1 to 2, so I would have to put an edge between the singleton sets. And similarly, I have another edge between the singleton set 2 and the singleton set 3. And then one can check that actually these are all the edges in this example. We just have 3 edges in the Powerset graph in this example. We have here another example. This time I have the oriented 3-cycle. I want to illustrate with this example 2 observations. The first is, I claim for every digraph H, there is a homomorphism from H to the Powerset graph. How would we do that? Well, I claim, this is what we've seen for the singletons in the previous example happens in general. I always have a copy of the original graph on the singleton sets. It's quite easy to see. So yes, I can homomorphically map H to P of H. Just map 1 to the set containing 1. On the other hand, I claim not for all graphs H we have a homomorphism in the other direction. We might or might not. An example is given here, actually. So we have not fully computed P of H yet. So let's fully compute P of H. We have an edge from 1 to 2, an edge from 2 to 3. So yes, there is an edge between the set 1, 2 and the set 2, 3. Similarly, and this is already unlike the previous example, here we have an edge from 2 to 3, but we also have an edge from 3 to 1. So there's no lonely vertices up there, so another edge. And finally, we have an edge from 3 to 1 and from 1 to 2. So we also have an edge back in the Powerset graph. So we see another copy of C3 sitting there in red. Is this all? No, in this example we have another edge. We forgot one edge. I claim that there is a loop on the set containing all 3 vertices, because every vertex has an outgoing neighbor and an incoming neighbor, which tells us that there is a loop on the set 1, 2, 3. And this is precisely the proof why not for all H we have P of H to H, because there is no loop in C3, but we have a loop in P of H. So there is no homomorphism from P of H to C3. From P of C3 to C3 there is no homomorphism. And now comes the link between the arc consistency procedure, and the Powerset graph. So let H be any finite digraph. Then I claim that the following are equivalent. Arc consistency procedure solves CSP of H. This is the goal that we formulated at the end of the first part today, before the break. That's what we are interested in. Is equivalent to the Powerset graph of H homomorphically maps to H. Note that interestingly, this second item you can decide on a computer, right? Because you can certainly on a computer compute P of H, and then you can try all possible homomorphisms from P of H to H and see whether there's a homomorphism. Whereas the first item is a priori not clear how to decide on a computer given H. No? So this is really an effective criterion that we present you here. And before we prove it, let's see whether the theorem fits the data that we have. Actually, for the first example, we don't have data yet. For the CSP of P2, we have not yet discussed whether arc consistency solves the CSP of P2. But I claim the Powerset graph of P2 homomorphically maps to P2. So we have the first consequence. We will learn from this theorem that arc consistency solves CSP of P2. To see that, let's go back. I will show you in blue the homomorphism from the Powerset graph of P2 to P2. How do we do it? Well, here we map every singleton to the element it contains. And then we have a little more to do for the two-element subsets. For instance, I could map this here and this here. And the isolated vertices, I could map them wherever I want. So certainly I have a homomorphism from the Powerset graph of P2 to P2. Back, check. The Powerset graph of T3 homomorphically maps to P3. And the arc consistency procedure solves T3, CSP of T3. There's a little bit to check here, so I leave you this as an exercise. It's doable. Please do it. The third item, on the other hand, we've done already. We have seen P of C3 has a loop, C3 has no loop, so there's certainly no homomorphism. At the same time, CSP of C3 is not solved by arc consistency. That's what we've also seen before the break. So check. The theorem also explains this example. To prove it in general, we rely on the following lemma. And this lemma is really very easy and links the formulation of the arc consistency procedure with the definition of the Powerset graph. Also note, look what's written there. We say arc consistency on the left. Arc consistency procedure for H does not derive the empty list on G. This is precisely the situation we are interested in. Because if the arc consistency procedure does derive the empty list on G, we already know there is no homomorphism from G to H. For sure, we say no. This is the easy part. So the interesting part is precisely what's written there. Arc consistency does not derive the empty list. This is what we are interested in. And on the right it says, this is the case if and only if our input graph G homomorphically maps to the Powerset graph of H. So we first prove this lemma, and then we prove the theorem. Both directions of the lemma are easy. Let's look at one of them at an example. Suppose we run the arc consistency procedure for the directed version of P3 on this example input graph G that I've drawn on the left. So what would the arc consistency procedure do? In the beginning, it has a bag with all possible values for each variable. We have 0, 1, 2 everywhere, 0, 1, 2. And then it would start eliminating values. As I've explained before, it would eliminate 2, at these vertices, and then it would even eliminate the value 1 for the lower vertex of G here. Dually, we would eliminate 0 from the top, 0 from the middle, and 1 from the top. On the other hand, for these two vertices on the right in G, we can't eliminate so much. We can still eliminate 2 from the bottom vertex and 0 from the top vertex, but not more. Okay, so the lemma claims that there is a homomorphism from this graph G into the Powerset graph of P3. And actually the idea is quite simple. Where do we map? We map every variable of G to the set of values that remains. So for example, this variable on the right is mapped to the set 1, 2, which is non-empty because the R-consistency procedure did not derive the empty list. So there is a vertex 1, 2 in the Powerset graph for P3. Likewise, there is an edge, there is a vertex 0, 1 where I can map the variable at the bottom of the right here. And now I have to verify that this is in fact a homomorphism. And if you check out the definition, go back, how were the edges defined? The fact that the R-consistency procedure did not remove a value from the variables tells you precisely that there must be an edge where there should be one. Now this you have, either you see it or you will see it if you look slowly into the script, but this is really a matter just of checking the definitions. This blue thing is a homomorphism. Now comes the other direction of the lemma. Suppose that we have a graph G which homomorphically maps to P of H. We claim that the R-consistency procedure cannot derive the empty list. We claim that every element which lies in the image of H, remember, in the image of H we have elements of the Powerset graph, so this will be vertices of H. We claim that all of those elements will never be removed from the bag for that variable. Why is that? Suppose the R-consistency would remove one of those elements. For instance, we are interested in this value. Suppose the R-consistency removes it, and this would be because of some edge along which we could perform a local inference. But at the same time, also note that H is a homomorphism. So this edge must also be mapped to an edge in the Powerset graph. By assumption, right? We said G homomorphically maps to P of H. So we have an edge between these two blue bags. And now if you look into the condition how the edges in the Powerset graph are defined, this means precisely that in particular for this red vertex here, there is a neighbor in the other bag. So in fact, our consistency cannot remove the value. So again, it's basically, the proof is basically just a matter of checking the definitions. Okay, now we have the lemma. Now we can try to prove the theorem. We have to show that our consistency procedure solves the CSP of H if and only if the Powerset graph of H homomorphically maps to H. We start with the forward direction. We have to prove that the Powerset graph of H homomorphically maps to H. So what we do is we run the R-consistency procedure for H on P of H. P of H is the input to the R-consistency procedure of H. Okay, what will be the outcome? We certainly know P of H homomorphically maps to P of H. So the lemma gives us that the arc consistency procedure does not derive the empty list. Not derive the empty list. Hence, the assumption implies AC solve CSP. The assumption implies that P of H homomorphically maps to H. Since the arc consistency procedure is correct, it did not derive the empty list. So, P of H homomorphically maps to H. Now let's look at the other direction. We assume P of H homomorphically maps to H. Now we have to look at two cases. Now we want to prove arc consistency solves CSP of H. If we have a graph G, if arc consistency H derives the empty list on G, then we certainly know, and this is always true, G does not homomorphically map to H. On the other hand, if the arc consistency procedure does not derive the empty list, on an input graph G, then by the lemma, this time the other direction of the lemma, we know that G homomorphically maps to P of H. But P of H homomorphically maps to H. And since homomorphisms compose, we have G homomorphically maps to H. And that's precisely what we want. We want that the arc consistency procedure gives the correct answer, and it does. End of proof. Now this is an excellent occasion to train a little bit how to apply this theorem. So this is certainly that I want everybody, at the end of the course, everybody should be able to determine for a given graph H whether the arc consistency procedure will solve CSP of H. For instance, if you look at the following graph H, does the arc consistency procedure solve CSP of H? Well, you would start as follows. You would name the vertices of H, and then you would start creating the vertices of the Powerset graph. Oops. And you would try to figure out where there are edges. And it would be a bit of a work. And at the end, you would have to try to see whether there's a homomorphism from this resulting thing into H. It's certainly maybe not immediately visible, but doable once you do the work, right? So it's a very instructive procedure how to find out whether the arc consistency procedure solves your problem. So please do this exercise. It's excellent. Yeah? In this video, I want to treat yet another perspective on the arc consistency procedure, which is very important. It's called tree duality. Let me start recalling an example that we've already seen. We were interested in the question earlier whether G homomorphically maps to P1. P1 was really simple. The CSP of P1 is really simple. It amounts to checking whether there's a vertex which has both an incoming neighbor and an outgoing, an incoming edge and an outgoing edge. So we sketched the proof that this is the case if and only if P2 does not homomorphically map to G. Now you see on the left I have a homomorphism, on the right I have a non-homomorphism. This is sometimes called a duality. And there are many more dualities. I claim that P2 in the directed version has a duality. I claim that a graph G homomorphically maps to P2 if no vertex Zi homomorphically maps to G. I have to define you Zi. Z stands for zigzag. Z1 is simply P3. It's clear if P3 homomorphically maps to G, G cannot homomorphically map to P2. Longer paths don't map to shorter paths. Z2, and now it's really becoming visible why it's called zigzag. Z2 goes up twice, then makes a little zigzag and goes further. So it also has 3 levels, but it's a little bit wider. Note that there's a homomorphism from Z2 to Z1, but not in the other direction. Okay, maybe you can already imagine what Z3 is. It goes up twice, makes 2 little zigzags, and goes further all the way. Also note that Z3 does not homomorphically map to P2, since Z3 has 3 levels, but P2 only has, well, Z3 has 4 levels, say, and P2 only has 3. Okay, so this duality needs proof, of course. I'll not give it to you, I just claim it's the case, but it's true. And another duality comes from T3. Also the graph T3 has a duality. Here it's a simple one, a finite duality. A finite graph G homomorphically maps to T3 if and only if the path P3 does not homomorphically map to G. A digraph H has tree duality if you have a set of orientations of trees. So a tree is an undirected graph which is connected and has no cycles. An orientation of a tree is a tree where you give an orientation to each of the edges in an arbitrary way. So the paths that we've seen are examples of orientations of trees, but also the zigzags are examples of orientations of trees, and there are more. There could be branching going on. Okay, so H has tree duality if there's a finite set of orientations of trees such that for every graph there is a homomorphism from this graph to H if and only if no orientation of the tree from our class N stands for no, no, forbidden, none of those oriented trees homomorphically maps to G. This is the definition of tree duality, and this is closely linked to the arc consistency procedure. So our new theorem adds a third item to describe the power of arc consistency. Arc consistency solves CSP of H if and only if P of H homomorphically maps to H, that we've seen, if and only if H has tree duality. We've already proved 1 and 2 are equivalent. So we can prove everything in cyclic order actually, and it's fully in the script. If you want to, here we'll only sketch it. We are close to the end of today's video lecture. 3 implies 2. Since H we assume has tree duality, it suffices to show that whenever you have a tree, an orientation of a tree T, which homomorphically maps to P of H, it also homomorphically maps to H. And this is actually something that you can prove inductively. And it's a little bit technical, but relatively easy. The implication from 1 to 3 is maybe more interesting. Suppose arc consistency solves CSP of H, and suppose the arc consistency procedure derives the empty list on some graph G. Then you can, in some sense, imagine the derivation of false as some sort of tree-like structure. Why? It's a proof tree. You make some inferences, and some inferences might depend on some other inferences, and so on. So you chain the inferences, and what shows up is a proof tree, and at the end of the proof tree there's the empty list. That's how you should imagine a run of the arc consistency procedure. It's a tree. And that's how trees show up in this theorem, and that allows you to prove the implication from 1 to 3. So this was just a sketch, and please check out the script for details.